He was sickly, poor, and half-blind. His father was a mercenary who abandoned the family. His mother was accused of witchcraft and dragged from her home in the middle of the night, hidden inside a wardrobe. He was chased from city to city by religious persecution, lost his wife and child, went unpaid for years, and died on the road, far from home, looking for work. And yet this man, Johannes Kepler, discovered the laws that govern how planets move through space. He took the universe apart and found the mathematics hiding inside it. He did what Copernicus started and what Galileo championed, but what neither of them could finish. He found the shape, the actual, precise, provable shape of the solar system. "I have confirmed its veracity," he wrote, "and I admire its beauty with boundless and soul-stirring delight." That sentence tells you everything about who Kepler was. A man torn between the mystical and the mathematical. A man who believed, with his whole being, that God had built the universe according to a hidden geometric perfection, and that it was his sacred duty to find it. He was wrong about many things. He cast horoscopes. He believed the planets made music. He tried to fit the solar system inside a set of nested geometric solids, like some kind of cosmic puzzle box. But when the data told him his beautiful theories were wrong, he did something that most people, in any century, find almost impossible to do. He listened to the data, he threw away his assumptions, and he followed the truth wherever it led, even when it led somewhere no one had ever gone before. Kepler was born on December 27th, 1571, in the town of Weil, in the German state of Württemberg. His family was, by most accounts, a disaster. His father, Heinrich, was a soldier with an erratic, volatile personality who drifted in and out of the family's life before disappearing for good. His mother, Katharina, was a sharp-tongued, difficult woman who would later become the center of one of the most disturbing episodes in Kepler's life. The boy himself was frail from the start. Sickly as a child, he grew into a hypochondriac adult, plagued by real and imagined ailments, squinting at the world through weak eyes that would have made his later astronomical work almost comically difficult, if not for the fact that his greatest instrument was not a telescope, but his mind. He attended the University of Tübingen, where he studied under Michael Maslin, one of the few professors in Europe who openly taught the Copernican model of the universe. Copernicus had published his revolutionary work decades earlier, arguing that the Earth revolved around the Sun rather than the other way around. But most of the academic world still treated the idea with suspicion or outright hostility. Maslin was different. He believed Copernicus was right, and under his influence, the young Kepler became a convinced Copernican. Kepler had originally intended to become a theologian. He was deeply, earnestly religious, a Lutheran who took his faith seriously and never wavered in it. But after graduating in 1591, he accepted a teaching position in Graz, in the Austrian province of Styria. He was not, it must be said, a particularly good teacher. His classes in mathematics and morals attracted few students, and his lecturing style left much to be desired. But the job gave him time, and time, for a mind like Kepler's, was everything. He spent his free hours doing two things: casting horoscopes, which he believed in without great enthusiasm, but which paid the bills, and studying astronomy, which consumed him entirely. In 1597, he published his first major work, Mysterium Cosmographicum. In it, he laid out his Copernican vision of a sun-centered universe. But he went further, much further. Drawing on the ancient Greek reverence for geometry, and particularly on the Pythagorean belief that all of reality could be expressed through numbers, Kepler proposed something extraordinary. He argued that the orbits of the 6 known planets were defined by the 5 perfect geometric solids discovered by the ancient Greeks. Inside the orbit of Saturn, he placed a cube. Inside the orbit of Mercury, an octahedron. Each planet nested inside its own geometric shape, the whole system fitting together like a divine puzzle. It was beautiful, it was elegant, it was deeply wrong. but it revealed something crucial about Kepler's mind. He was searching for the hidden architecture of the cosmos. He was convinced that behind the apparent chaos of planetary motion lay a deep mathematical order, and he would spend his life trying to find it. He sent a copy to Galileo. The Italian replied in a friendly but cautious tone. He wasn't convinced, but he recognized a fellow traveler. In 1600, religious persecution forced Kepler to leave Graz. As a Lutheran living in Catholic territory during the Counter-Reformation, his position had become dangerously precarious. He moved to Prague, where he found work as an assistant to the greatest observational astronomer of the age, Tycho Brahe. Brahe was everything Kepler was not. Wealthy, flamboyant, physically imposing, with a prosthetic nose made of gold and silver alloy to replace the one he had lost in a duel. He was also, and this is the part that matters, the most meticulous observer of the heavens who had ever lived. Over decades of painstaking work, Brahe had compiled the most accurate and comprehensive set of astronomical measurements in human history. His data on the positions of planets, particularly Mars, was unmatched. The relationship between the two men was, predictably, difficult. Brahe guarded his data with ferocious jealousy. He wanted Kepler's mathematical genius, but he wanted it in service of his own model of the universe, not Copernicus's. He doled out information in small, carefully controlled portions, never giving Kepler enough to work with independently. And then, in 1601, Brahe died, suddenly, unexpectedly. And Kepler inherited everything. The treasure trove of observations that Brahe had spent a lifetime accumulating was now in the hands of the one man alive who had the mathematical ability to unlock what it contained. And over the next 8 years, that is exactly what Kepler did. He started with Mars. Its orbit had always been the most troublesome, the one that refused to fit neatly into either the Ptolemaic or the Copernican model. Kepler threw himself at the problem with an intensity that bordered on obsession. He tried one hypothesis after another. He calculated, recalculated, and calculated again. He spent years grinding through the numbers, testing every possible arrangement of circles and speeds against Brahe's data. And one by one, his assumptions broke. The first to go was the most ancient and sacred of all astronomical beliefs, that planetary orbits are perfect circles. From the time of the Greeks, through Ptolemy, through Copernicus himself, everyone had assumed that planets moved in circles or in combinations of circles. It was a philosophical conviction as much as a scientific one. Circles were perfect. The heavens were divine. Therefore, celestial motion must be circular. But the data said otherwise. Mars refused to move in a circle. No matter how Kepler adjusted his calculations, the circular orbit was always slightly off. The discrepancy was small. Most astronomers would have shrugged and blamed observational error. But Kepler trusted Brahe's measurements. He knew they were accurate. And if the observations didn't fit a circle, then the orbit wasn't a circle. At the same time, he abandoned another ancient assumption, that planets move at constant speeds. This too was a philosophical inheritance from the Greeks. Uniform motion was considered noble, divine, fitting for heavenly bodies. But again, the data was clear. Planets speed up as they approach the sun and slow down as they move away from it. The motion was not uniform. It was variable, governed by proximity to the central star. Through years of relentless trial and error, Kepler discovered the mathematical law that described this variation. An imaginary line connecting a planet to the sun sweeps out equal areas in equal intervals of time. When the planet is closer to the sun and moving faster, the line sweeps through a short, wide arc. When the planet is farther away and moving more slowly, it sweeps through a long, narrow arc. But the area covered is always the same. This became Kepler's second law, and then came the shape. If the orbit wasn't a circle, what was it? Kepler tried oval after oval, curve after curve, testing each against Brahe's data. And finally, he arrived at the answer, an ellipse. a geometric figure the ancient Greeks had known about but never applied to the heavens. Planetary orbits are elliptical, with the Sun sitting not at the center but at one of the two focal points. This was Kepler's first law, and with it, 14 centuries of circular astronomy collapsed. Both laws were published in 1609 in his work Astronomia Nova. The title means the new astronomy, and it was exactly that. What Kepler had done was not simply to correct a few calculations. He had redefined the purpose of astronomy itself. Before Kepler, astronomy was essentially a prediction machine. It tracked where planets had been and calculated where they would go next, without asking why they moved the way they did. Kepler introduced the concept of physical force into celestial mechanics. He understood that something was acting between the Sun and the planets, pulling them, governing their speeds, shaping their paths. He thought the force might be magnetic. He was wrong about that. But the insight that the heavens operated according to discoverable physical laws, not divine whims or geometric perfection, was revolutionary. He had come breathtakingly close to the law of universal gravitation. That final step would be left for Isaac Newton, who would later acknowledge his debt to the sickly German mathematician who had done so much of the groundwork. A decade later, in 1619, Kepler published what he considered his masterpiece, Harmonices Mundi, the harmony of the world. It is, by modern standards, a strange book. Overflowing with illustrations and musical notation, each planet assigned its own scale of sounds. It reads at times like the work of a visionary, and at times like the work of a man lost in mystical reverie. Kepler argued that mathematics offered a direct pathway to understanding the mind of God, that the proportions governing the cosmos were the same proportions governing music, and that humanity, through discovering these laws, could share in the divine vision of creation. It is tempting to dismiss the book as eccentric, but buried within its pages, almost casually, is one of the most important discoveries in the history of science, Kepler's third law. The square of the time it takes a planet to orbit the Sun is proportional to the cube of its average distance from the Sun. This elegant relationship links the orbital periods of all planets to their distances, binding the entire solar system together with a single mathematical thread. Newton would later use it as one of the foundations upon which he built his theory of gravity. Beyond his astronomical work, Kepler wrote important treatises on optics and published the Rudolphine Tables in 1627, a comprehensive catalogue of known stars based on Brahe's observations that remained in use for well over a century. His Epitome of Copernican Astronomy, published between 1619 and 1621, was promptly placed on the Catholic Church's list of banned books. The irony was not lost on anyone, a devout believer whose work was condemned by the institution he revered. And through all of this, Kepler's personal life was a catalogue of suffering. His first wife and child died in 1611. The following year, his patron, Emperor Rudolf, abdicated after a rebellion, and Kepler was out of a job. He moved to Linz, worked as a mathematician, then fled again around 1625 to escape religious persecution. He returned to Prague in 1627, was hired as an astrologer for the Duchy of Sagan, and then left once more, restless and possibly disillusioned. He died in Regensburg, Bavaria, on November 15, 1630. He was 58 years old, broke, and still looking for a position. And then there is the matter of his mother. Katharina Kepler was publicly accused of witchcraft, in an era when such accusations were not merely social embarrassments, but potential death sentences. When women were routinely tortured and executed on the flimsiest evidence, the charge was devastating. Katharina, combative by nature, filed a lawsuit for slander. But the Counter-Reformation had created a climate in which witch trials were practically an industry. A formal indictment was drawn up. In 1617, Kepler wrote petitions on her behalf, demanding that her name be cleared. In 1620, at the age of 74, Katharina was arrested in the middle of the night and taken from her home, concealed inside a wardrobe. She was threatened with the wheel, the medieval torture device that shattered bones and crushed the body. She refused to confess. Eventually, she was released, but she died just 2 years later, broken by the ordeal. And here is the strangest part of the story. Some of Katharina's torments may have been caused inadvertently by Kepler himself. Around 1610, he had written a manuscript in which he described, apparently in fictional terms, his mother communicating with demons from the moon. This manuscript would eventually become the basis for his posthumous work, Somnium, The Dream, a remarkable piece of speculative fiction in which Kepler imagines a journey to the lunar surface. What he finds there is not a utopia, but a nightmare, a world scorched on one side, frozen on the other, inhabited by giant serpents, some winged, some crawling across barren rock. It is one of the earliest works of science fiction ever written, and it may have helped put his mother in chains. Kepler was a man of contradictions, a devout Lutheran who undermined the authority of the Church through his discoveries, a mystic who surrendered every beautiful theory the moment the data contradicted it, a man who heard music in the orbits of the planets and then, with brutal mathematical honesty, proved that those orbits were not the perfect circles the music seemed to demand. Albert Einstein, centuries later, wrote about Kepler with deep admiration. He praised him as one of those rare individuals who proved simply incapable of doing anything other than fiercely defending their convictions in all areas. Einstein recognized in Kepler a fellow spirit, a man who freed himself from every intellectual tradition into which he was born. Not just the religious tradition, not just the authority of the Church, but the entire inherited framework of assumptions about nature, about the limits of knowledge, about the relationship between thought and observation. Kepler broke all of it, quietly, stubbornly, through years of painstaking calculation and personal misery. He dismantled the ancient certainties and replaced them with something truer. He didn't live to see the full consequences of what he had done. Newton would build on his laws. The entire science of orbital mechanics, everything from satellite launches to interplanetary probes, traces back to the 3 laws Kepler wrested from Brahe's data in a cold study in Prague. He was sick, poor, persecuted, and grieving for most of his adult life. He never achieved the fame that Galileo enjoyed, or the reverence that Copernicus received. But without him, neither Galileo's observations nor Copernicus's model would have amounted to more than an interesting idea. Kepler gave the heliocentric universe its skeleton, its actual, mathematical, verifiable structure. He showed that the cosmos was not built on divine circles and uniform motion, but on ellipses and varying speeds, governed by forces that could be measured and understood. He heard the music of the spheres, and then he proved that the real music was even stranger, even more beautiful than anything the ancients had imagined. That was Johannes Kepler.